Hello, everyone. This is lecture 19 of PTRE 475575, well completions and advanced stimulation techniques. We have about 10 to go, and we might miss one or two because of I'll be gone out of town, so I will have to review, record or something. Yeah. I did post homework free, and it will be due on Monday, and we'll go over it today. It's not too difficult, to be honest. And I did make a mistake when I was talking in the class. I thought this class has 5 homeworks, but it's really 4. So we have this one and then another one to go, and that's it. From my understanding, I don't think I have anyone hidden unless I'm missing something. But yeah, we're approaching the end. Our second midterm will be, I think, in April 19 or 16, something like that. And then you guys have the term paper, which is coming up fast. It's about in 5 weeks. And then, and then we are basically wrapping up. We will have the final on May 16 or something, or May 12, I don't remember. And that's it. The homework is easy points to collect. So let's start with that, because you already know how to do it. And we have this lecture, the next lecture, office hours tomorrow, and then it's due on Monday, basically. So we have a lot of time to make sure that you guys, what you have is good before you submit it. You guys have a lot of time. So homework 3. Okay. So due on Monday, April 6, 26. For 10 points, in context of hydraulic fracture optimization, which is the optimal geometry trajectory that the lateral, i.e. the horizontal section of a horizontal well should be drilled along, and why? We have been talking about this during the lectures, that it's even mandated by law in Louisiana to drill your well in this direction. And there is a reason for that. So 10 points for that. Ignoring the impact of wellbore in the surrounding stress field, what is the minimum fluid pressure required to induce a tensile fracture oriented transversely to a horizontal well drill parallel to SH mean? So ignoring the impact of the wellbore, that's a key word, that's a key phrase. It means that act as if the wellbore is not there. So don't give me answers that have to do with near wellbore stresses, those sigma, theta, theta, sigma, RR, sigma, ZZ. I don't care about those. The only thing I care is the stress I'm fighting to open a fracture. And remember that the well is drilled parallel to SH mean. So the fractures are opening in doing work against what stress. And then also, it's not just enough to do work against that stress you are opening against. It's also, you need to also do work against the tensile strength of the rock. So that should be your answer. Your answer should be very simple, actually. Why is the hydraulic stimulation of long horizontal laterals divided in stages? And I did mention that in class, but I didn't give it a lot of emphasis. The reason why we don't to the entire well and we divide it into stages, think logically, like, why do we break it into stages? Like, otherwise, what kind of fracture or friction gradients I'm dealing with? What if I do the whole well as a one stage? The pressure here, presuming I'm closer to the heel, will be much higher than the pressure at the top, right? Big differential. So what will happen? It will be I will be getting more fractures where the pressure is high, and then I won't be getting any fractures where the pressure is low. So I divide it into stages and I stimulate them successively or following a plan. Question number 4. By the way, stop me if you have any questions. Why would the actual fracture initiation pressure likely be different than what the answer to question number 2 suggests? I mean, what are you having on question number 2? What are you assuming there? Ignoring the impact of the wellbore. So that's kind of important. This is the way you need to think. I'm not saying that this is the answer. I'm saying that's the way you need to think. Question number 6. No, number 5. What is the formation breakdown pressure and what is its signature in regard to surface monitoring? What is its importance regarding what goes on downhole? Let me just see this homework 3. And okay, let's see. No, that's the old one. Yeah, I don't have it on my phone, but so remember that diagram that we saw? It was, I think, green, and it's like, what is the formation breakdown, and what does it physically represent, and what is its signature in regard to surface monitoring? What am I reading on the surface? Basically, that's what I'm trying to find out. And why is it important in regards to what goes on downhole? It's the highest pressure that the well will ever encounter, bearing anything out of the ordinary. It's also the highest pressure at which I have fracture initiation. It's the end of the pressure window at which I have fracture initiation, starting from leak of pressure all the way to breakdown pressure. And what really happens at breakdown? Like, what does it signify, physically speaking? Why is the plane, i.e., orientation in space, of fracture initiation often different than that of the final propagation plane? So, why do often the fractures will start one orientation and then switch into another? And that is, think about question number 2 about that, actually. Now, I want you to explain these 10 points. So it's not enough to drill my well in the direction that I want to get transverse fractures. I may still get longitudinal. And then I get that thing that we saw from module 1 when the fracture initiates one way and then twists to get the other orientation. And then the twisting is bad. It's bad when it comes to production. It's bad when it comes to proper placement. It's bad for several reasons. For ball-activated multi-stage frag jobs, why is it important to know the diameter of the balls used in each stage? I think Aaron Barton, in the videos that we saw, he made it clear why does the size of the balls that we use matters, and why we go from big size to small size accordingly as we go from toe to the heel when we fracture a well. Question number 8. Why is it important to know the dimensions and profiles of tools before sending them downhole? There is a reason for that. Why do we need to know the dimensions of the tools? It has to do with fishing, so that we know when they are being cut and they are staying downhole, what we need to fish, what tool are we gonna use to fish them out. Using the KGD model, calculate fracture half length, L, fracture width at wellbore, WW0T, and fracture net pressure at the wellbore, P net, after 30 minutes of pumping at 25 barrels per minute. 1 barrel, I'm giving it to you as 0.0026 cubic meter per second, with the hydraulic fracture height reaching 30.5. The rock Young's modulus, is 61.4 GPa, which translates to 61.4 times 10 to the 9 GPAs. Typical rock Young's modulus, and its Poisson's ratio is 0.25, with a viscosity 1 centipoise, which translates to 1 millipascal second. Ignore any effects from fluid leak-off from the fracture into the adjacent rock formation. Okay. Any questions so far? Okay. And question number 10, that is the longest one. You are going to need a spreadsheet for that. It's not that hard. Is calculate the net present value for a hydraulic fracture treatment project costing $150,000, expected to yield the following production rate, flow rate. I'm giving you an equation, which is like the hyperbolic decline, where the B factor is 0.5 and the initial decline rate is 0.75 per year, with the initial production flow rate at 300 stock tank barrels per day. Assume that the production flow rate, QT, remains constant over a 365.25 day year. T refers to the years elapsed since the start of the project on year 1. The treatment and QI took place on year 1. Consider the project lifetime of 15 years and a discount rate of 12% per year, i.e. 0.12 per year, and a constant oil price of $50 per stock tank barrel. When I wrote this homework, it was like 2 years ago. There are no sale plans for any production from this well. Present your results in a nice table and make a plot of NPV variation against time. So, year 1, year 2, year 3, all the way to year 15, right? Okay. Year 1, I have a cost that is $150,000 to fracture my well. okay, typical prices. And then I make for the entire year something like 300 stock tank barrels per day, okay? Now that is year one. So year one is not discounted, right? It's not discounted. We see it, homework. So because it's year one, it won't be discounted. I had it in front of me and now, let me see. So 300 stock tank barrels every day. And basically, how do you call it? Every year is gonna be something like 109,000 barrels per year, and then you're gonna sell those barrels at $50 each barrel, and it should not be discounted. You get the net present value or the present value for that year. Then we go to year two. Year two, do I have any cost? No. Do I have any production? Yes. The production is no longer gonna be 300. It's gonna be QT, which is basically Q2, 300 divided by 1 plus B times D. B is 0.5, DI is 0.75, T is, what is the T? T refers to the years elapsed since the start of the project. So it's gonna be 2 minus 1, 1. So T is 1. And you solve for the rate, which should be smaller than 300 stock tank barrels. You translate that to, it's like 159. You translate that to yearly rate, so times 365.25 becomes something like 58,000 barrels of that year. And you will get $50 for each barrel. So you can calculate the total amount of money you are going to make that year. And then you need to subtract the money that you are going to pay, which is zero in this case. So you take the value, the final value, which is basically the revenues, and you do, you take out basically the interest. So you do that value divided by 1 plus t to the power, IR to the power of t, which in this case, IR is going to be 0.12 to the power of 2 minus 1, so to the power of 1. So you divide by 1.12, which makes this value smaller. So the revenues on the second year, the cash flow is something like, what is it? It's like almost 3 million, something like that. And then you basically take those 3 million, let's say, you do divided by 1.12, it's going to become a smaller value. And then you add that to what you accumulated from the first year. But remember, the first year, you didn't take the interest out because it was the first year. You didn't discount. The second year, you discounted. The third year, we are going to discount even more. It's going to be 0.12 to the power of 2. and then it's going to be 0.12 to the power of 3 to the power of 4. So you discount more and more every year. And then at year 15, you're basically making only something like, I calculated it as 8 barrels a day on the last year. And it's going to lead to something like the cash flow would be like 140,000. And then you basically, it doesn't add a lot to the cash flow, to the NPV, but it does, you know, I mean, it does something. And yeah, I want you to show me how NPV will vary with time, basically. And I'm expecting the NPV will either start negative or at a small positive value, and then you add more, more, more. But every time you add, it's going to be less and less, you know, that you add. Until year 15, until the end of year 15. And you should give me something like in the orders of $10 million. By the way, this is a very good well. It looks, I try to encourage you, and it's a, look, such a bad oil price, 15 barrels a day. Not an amazing well. 300 barrels a day is pretty good, actually. 300 barrels a day is pretty good, but it doesn't decline very fast. That's the thing. So it keeps going, and it gives you like a nice effect. It's gonna, if that was, if you get a well like that, you don't need to work a day in your life. Let's put it this way. So start early. Let me know if you have any questions. I have office hours tomorrow, and I'm available by email. We have lecture on Thursday. I can answer questions there, and then we can basically proceed. Yeah. Questions number 9 and 10 are gonna be the longest. So if you do the easy ones before, would be great. Question number 9, it helps you use those models that we learned, those ugly equations, and it makes it easy for you to use it. So you are using only like SI units, which is good. Because if you do it consistently, you just don't need a conversion factor. I will say you have to change barrels per day to cubic meters per second, change GPA to PA, change CP to Pascal second, and then it's all SI, as far as I know. So you should be good to go. And with question number 10, take your time. It's basic economics. It's basic economics. I want the income to come as early as possible, and I want the payments to be delayed as much as possible, although I cannot do much in this case. I have to do a fractional job and then pay for it immediately. Otherwise, doesn't really make much of a, I cannot delay the payments, but yeah, other projects I can. Anyway, any questions? Okay.
No, Professor, thank you.
Let me know if you have any issues moving on. Okay, back to our grade module 3. We went pretty far last time. I think we made it, we are not far from the end. We did talk about economics. And this is basically what you are gonna draw for me. Although for you guys, because the well is producing a lot the first year, it makes its money very, very quickly. So it's gonna make more money than what it costs from year 1. So we really start pretty positive from my understanding. And as you see, as you go up, as the time goes by, the rate drops, but you don't have any additional cost. So you keep going Rain drops, and then you basically go to a flat line. That's when you the, that's when basically towards the end of the life of the well, the only cost that you need to worry about is what we call LOE, lease operating expenses, some maintenance fees for keeping the surface facilities in play up to date, like everything clean, everything functional. And this is not a lot of money. Have somebody go in and check the well every month or something, every week. This doesn't cost much. But once the well starts making less money than what you need for those LOE, lease operating expenses, then the well is not profitable to be running. You just want to plug and abandon. At that stage, you're gonna make a plan on how you are gonna plug and abandon your well, pull out of it whatever you can that you can sell probably to make some money. And then, yeah, that's it with the well. And hopefully you did a good plug and abandoning job. You don't want these wannabe railroad commissioners to be after you. That wouldn't be nice if if the well comes alive on its own a few years after because a neighbor of yours is doing a water flood.
I have a question,
Yes,
Professor.
sir. Yes, sir.
So from the diagram in front of us, when the decision to do, for example, water injection or refracture?
That's a good question. So, say for instance, I think it's a good idea to do a refracture somewhere here. Okay. It doesn't matter which color is the line. Okay. Say I'm gonna make a refracture 5 years in. The refracture is gonna cost me maybe 100,000 or like $200,000 if the original fracture costed me 150. But $200,000 is gonna be a cost. It's gonna be a cost, but it would be also discounted. When I'm measuring the net present value, I'm measuring the net present value today. So it's gonna be as I'm adding up, this is adding up, and then it will go down because I'm spending this $200,000, and then it's going back up again. Hopefully at a higher slope than before because of the hydraulic fracturing. But basically, it's gonna be like a dip because of the money I spend. I have new cost to worry about, 200,000. But say it's gonna be, we said in 5 years, it's gonna come to my calculations as it's gonna be a minus 200,000 divided by 1 plus 0.12 all to the power of 4. So it wouldn't be minus 2,000. It would be minus less than 2,000. But after that, the well, if I did a good refrac, the well would be producing much faster than before, much higher flow rate than before. So I hope that it's gonna help me make up the money. So it's gonna go back to those 300 or like maybe 290 or something. That's the how do you say that's the dilemma I have. Like if I'm gonna refrac, pressure is gonna rate is I'm gonna pay money, but I hope that the rate is going up and that the rate is gonna go up enough to make sense for the money I spend for the refrac. And of course, I want the refrac to be successful. And yeah, I mean, that's about it with the economics, to be honest. It's just a normal project. It's just the costs are coming up early, and then it's just revenues afterwards. Um, and of course, like I said earlier, Region 1 is much smaller and narrower than Region 2. And in real life, discounting takes place throughout the entire year. So it's not discounting only like for the first year, and then second year is like on December 31st, I make 300 wells. I produce 300 wells. Those are not discounted because it's still year one. And then I move to year two, January 1st of the second year of the project. I produce something like, what did we say? It's going to be I forgot. From 300, I dropped to 159. And then those are going to be discounted by 12%, basically, because it's one day after, but it's year two. It's a more smooth calculation that the accountants are doing when they are doing these estimations, oil and gas accountants. For us, because this is a class example, like for your homework, it's almost like first year, day one, I do the frac job, and day one, I'm producing 365.25 times 300 barrels. So it's like as if all the production comes from the first day, as if same thing with all the cost. And then second day, second year, first day of the second year, I do 365.25 times 159. And then I get how many barrels I'm producing that year times divided by 1.12, and then so on and so forth. So basically, every year you need to be asking yourself, do I have a cost and do I have a revenue? And for you guys, only the first year you have a cost. Every other year you have revenue only, except the first year where you have cost and revenue to worry about. It's a very, very simplified project. And that's why it looks very good on paper. It's a little bit better than what it should have been, you know. But you understand how people will even stripper wells, which is basically less than $10, 10 barrels a day, they still can make money. I mean, this is basically a stripper well. It becomes a stripper well on year 13, if I did my math right. That's when you drop below 10 barrels a day, and it's still making money. Like, if my calculation is right, which it should, between year 13 and year 15, I make something like 6 to 7. Something like 60 to $70,000 in the last 3 years of the well's life without any cost, which is not a bad, I mean, which is not a bad amount. Now, in real life, yes, there will be some costs, but it wouldn't be crazy. It wouldn't be crazy. So it's like, even if it costs you like 10,000 a year to have that well, and I'm exaggerating again. I mean, you still make like 10 times 3 is something like 30, and then you make 70 in that year, or 60 on those 3 years in total. So you gain the last 3 years of the life of the well something like $30,000, which is not bad. You certainly can live with it from a stripper well. that nobody cares about. Anyway, if there is no other questions, I will move on to the next subtopic, which is unfortunately a little bit more technical than what we have done so far, and maybe gets a little bit drier, but it's a topic that we need to cover. Some of you are gonna get a job in hydraulic fracture modeling, and you will be dealing with this stuff. Some of you are gonna go to grad school and do something related to hydraulic fracture modeling. You better want to know this stuff very well. It's gonna help you. Some of you may be doing your term paper on hydraulic fracture modeling or a relevant topic. I mean, yeah, for sure, we need a lot to learn from that. So, so far, what we have done was fracture initiation. So I have my solid rock, and then I'm about to pop it open, and I cause hydraulic fracture initiation. Basically, I'm rupturing a solid intact rock. Fracture propagation is a little bit of a different problem. I have a notch, and I'm trying to extend it. I'm trying to extend a crack notch. Basically, I have an opening, and I want to make it elongate. So this is the problem I'm doing. It's a little bit more complex problem because that opening is basically a discontinuity that I have to incorporate in my system mathematically, analytically, or computationally, numerically, for my simulator, let's say. So there was a paper in 1921, I think it was titled Mechanics of Rupture by Griffith and A.A. Griffith. And that became sort of the father of basically mode one crack propagation in a linearly elastic, isotropic, two-dimensional solid. So in this one, we assume that the constant net pressure equals to P sub O, and the fracture half length of C, as we see here, is an elliptical problem. Fracture half length is C, and then everything else is the propagation happens along the x-axis. This is the way the fracture is growing, and basically it's opening against the z-axis, which is out of the screen of the paper, out of the screen basically, out of the plane of the computer screen that I'm looking here. From solid mechanics, you expect the fracture width to be proportional to the net pressure and the fracture half length, and inversely proportional to the stiffness of the medium that it is propagating in. So, for instance, when your TA Kalu is doing experiments on gelatin mixtures, we expect the fractures there to be very fat. Why are they very fat? Because the fracture, the stiffness, the Young modulus of the gelatin is much smaller than the Young modulus of the rock. So I'm expecting it to be much fatter, let's say. Now, solving Griffith's crack problem, from Navier's equation, the fracture's opening stress orthogonal to its propagation plane, sigma yy, and the opening displacement uy at the crack tip are given by the following. By the way, it's a 2D problem. We are not opening against the z-axis. We are opening against the y-axis. I forgot. We are propagating towards the x-axis, but we are opening against the y-axis. So here, this is the displacement along the y-axis and the stress along the y-axis. And we see the equations that are not that difficult because we have c, which is the half length. We have x is how far along the fracture. How far the crack tip is from the fracture initiation point. And then this is basically after long derivations that Griffith arrived into these solutions. So it's, I'm throwing them to you like that, but there is a lot of derivations behind it that you can find by going through the Griffith's paper, which is actually going to be very interesting. The solution of uy and sigma yy are elliptical equations. At x equals 0, which is the middle of the fracture, uy is given by this equation, 2 times p sub o, 1 minus Poisson's ratio square times c divided by e. And then the maximum fracture width would be 4 pi naught times 1 minus Poisson's ratio square times c divided by e. Notice that e is in the denominator. The larger the e, the smaller the fracture width, the WO. At x equals c, which is the crack tip, sigma yy at x equals z, c goes to minus infinity. And that is a problem with the Griffith theory, is that if you do his math, you are going to get the energy at the crack tip going to something like infinity. This is not easy to deal with mathematically. We don't want solutions that lead to that. We don't want solutions that lead to 0 too much. We don't want solutions that lead to infinity or minus infinity too much. Because it's very hard to deal with it afterwards. It's hard if I assume that the pressure on the crack tip is infinite. It will be more tensile than the rock. It's basically like telling you that the fracture won't stop propagating as we go on forever. It won't stop propagating. Beyond the crack tip, the stress is tensile. For example, at x equals 1.15 C, that's like 15% further than the fracture half length, than the crack tip. I get something like the stress would be like minus P naught, which is the net pressure, basically, which is a logical value. Sorry. Yeah, P net. I mean, it's a logical value to be like minus P sub O at 15% further from the active, and it's a solution I can work with, mathematically speaking. Now, the most important outcome of that paper is the concept of something called the stress intensity factor or the fracture toughness. Well, critical stress intensity factor or the fracture toughness. These two entities that you have on your screen now, they are not the same, okay? If I put critical stress intensity factor, it's going to be the same as fracture toughness. And I will explain how it is. I will explain so that you can understand. So the stress intensity factor of a mode 1 fracture is given by this equation. Okay, is the limit of sigma yy at the crack tip plus some margin times square root of 2 pi r on the limit as r goes to 0. So basically the tip is becoming smaller and smaller. This is the thing about it as a property of the fracture at the crack tip. Okay, this is what drives fracture growth. Okay, this is what is trying to make the fracture grow. However, distance from the point of a solid to the crack tip. Hence, for a line crack whose P net is constant and equal to P naught, Ki is given by this equation. It simplifies basically to this. But again, this is what drives the fracture to grow. This is what drives fracture propagation from an existing notch. Now, according to Griffith, there is a condition that will determine whether the fracture will keep growing or stop. And hypothetically speaking, if you are sitting down at home trying to write a fracture propagation model, this is what you are looking at. Every iteration, every time step, you are measuring this Ki. And you compare that to the KIC, which is a property of the actual rock that you can measure experimentally. If Ki beats KIC, then we are continuing to propagate. If not, we stop there. KIC is the fracture toughness or critical stress intensity factor, which is a solid property of the rock. We're going to talk about how we measure it. It's not easy to measure. And Ki is basically a property of the crack tip that changes with time. We need to make sure if we want the fracture to keep propagating that Ki is bigger than KIC and vice versa if we don't. KIC can be measured in the laboratory with what we call semicircular bending test, considering linear elasticity fracture mechanics. And this SCB test is very, very smartly designed test. You have a semicircular sample with certain dimensions, certain radius, and a notch of certain length made. In this case, we have something like A for the length of the notch. And then we put that, we make 3 points of contact for the semicircular bend sample. We put 2 rollers at the bottom at a specific distance between them. We make sure that the sample is of a certain thickness, and then we apply a stress load on top. We make this experiment on something called the true triaxial test, or normal triaxial test. So nothing fancy about it. There is a plate that moves slowly upwards. So you put the sample there, you make sure it touches the top and the bottom, and then slowly the bottom moves up. The bottom plate moves up. Slowly, 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 and then it cracks. The pressure, the stress at which it cracks, it's very important for our estimations. It was invented by Chong and Kurapa in Japan in 1984. Very, very smart test. Use a rock sample cut out in the correct geometry. This is the correct geometry. And place it in a uniaxial loading frame. I will show you one when you guys come over for the second lap sometime this summer. I think I'm gonna be the one teaching it. So I will show it to you. Record the maximum stress load applied on the sample at failure. We call this basically F max. And it's gonna be a value with pound force. So 1200 pound force. Okay, good. Then I take this value 1200, I put it in the equation, and I calculate basically KIC. And this is a project, how it looks like. And this is another one of mine, actually. I took this picture in my last advisor at University of Texas. He had a geomechanics lab. And we made samples of PMMA, that's bulletproof glass. And we tested them. And I think PMMA broke as a CB, but it was hard to break it as a Brazilian test. I have a video somewhere, I think in the later slides, of how it breaks. So basically, okay, we have a picture of the true triaxia. So I need to show you some stuff. Oh, sorry, normal triaxia. Roller, contact on top. This is what applies F. F is stress downwards. What happens is that the plate moves up. And then as it moves up, it makes eventually the sample to break. You don't see it move up. It moves like in 2 inches per minute or something. It's very, very slow. And there is a reason it's moving slow, is not to give any biased readings. But ultimately, the plate comes up. Now you see this hole here. This was a Hubble loading frame. It could go, I don't know the prices now, what's in today's money, but it used to go like 10,000 pound force, and it costed $10,000. So the job was you get a pound force for every dollar that you are giving. This hole here on the plate is for something that is basically a black pole here, and then something that looks weird like this, and then you have something else like this. Now, touching that part, that needle I showed, that needle I drew, is very sensitive. We call it the needle here is very, very sensitive. We call it LVDT, longitudinal something transducer. So it's measuring displacement from the beginning all the way to the end of the project. So anything that happens, it's measuring. In this case, we don't need it for this experiment, but we need it for other stuff. So it's good to have it if you have it. A low KIC implies a brittle solid material. A good example of that is glass. Glass is very hard to break, okay? So we call it low KIC. Okay? Brittle materials fracture easily, while ductile materials do not. Ductile materials, they like to deform, not to break. They are not brittle. In fact, clays in shales, they say they make the rock very, very brittle, which is not a good thing. Well, not a good thing when it comes to hydraulic fracturing, but good thing for other stuff. Rocks are generally very brittle, but clays in shales give them some relative ductility. And it's not really certain what makes clays so ductile, but people suspect it's clays. And this is an example of a material I created myself called urethane plastic, not to be confused with urethane rubber that is used for fiber optic cables. In this case, it was a solid material that couldn't break. It would deform and not break. If this happens, you are not dealing with a brittle material. And what you are measuring, if you try to convert what you are reading to KIC, it's going to be giving you a high value. And that high value is basically, it doesn't mean anything. It's at least how much it can withstand without breaking the material. And here I have an example of a test, skip verification of a PMMA test. Notice how, sorry for the bad quality, but look at the plate is moving up and you cannot see it. And eventually the sample will break very abruptly. And you see it goes, plate moves up, you don't see it, and then eventually it will pop. There you go. Still scary. But ultimately, this is what happens. Plate moves up, applies stress on the sample, eventually it cracks. And if you play that video slow motion, you will see that those pieces, they hit one of the rods that are on the holding the loading frame, the carbon loading frame that can handle the 10,000 psi, and then it basically breaks. Well, after it breaks, it hits those rods, and then I think it goes that way. I remember I told you last time about a summer internship program that I took part as a supervising student. I had my own students who are part of that program, one student every summer. And it was with him when we took this video back in 2015. I believe he went on to get a master's from Texas A&M, and I don't know where he's working now, but yeah, he was very, very good. Okay, any questions, or I will move on?
No, Professor,
Okay,
thank you.
yeah. So example problem number 1. Calculate the maximum width and stress intensity factor of a fracture, and I assume a mode 1 fracture, of half length 30 feet, filled with fluid that is pressurized to P-frac of 3000 psi, which is immersed in an elastic medium of Young's modulus E of 145 ksi, Poisson's ratio 0.25, which is a quarter, and SH mean is 2900 psi. So that's a little bit of a tricky problem because I'm expecting you to make some assumptions. Like I'm giving you SH mean, I'm kind of implying that the well is drilled parallel to SH mean, so it's opening against SH mean, right? And then there is another assumption somewhere. We're going to see later. So P net, oh yeah. So basically P net is going to be P frac minus SH mean. P net is P frac minus SH mean, and this is basically E net. So 4 times P net, this is basically 4 PO C 1 minus N square from before. Same thing, divided by E. Just now you don't have C, you have L, that's the half length. And then, yeah, everything else. Some unit conversions make the feet to inches, make the, if you're gonna use PSI, is pounds per square inch, absolute. So PSI will cancel each other with the bottom, and you will get something like inches. So less than 1 inch is the maximum width of that fracture. And bear in mind, that's a 30 feet fracture. That's like the people online, you can see how big the room is. It's not particularly big, but I guess Maybe this is 10 feet. If I'm less than 6 feet. So yeah, that should be the ceiling should be like I think I'm 5'11" or something. So let's just say 6 feet. Uh, the the it would be like a fracture as tall as this, as long as this room is tall, which is gonna be it's a pretty big fracture, and the highest it can. Oh, sorry. Yeah, that's but 3 times that even. So I guess the length of the room would be 30 feet. If the height of the room is 10 feet, yeah, 3 times that, 3 times the height of this room. So I'm saying that the maximum width of that fracture, of this fracture, is gonna be less than an inch. So you get the idea. And I made a mistake here. Discard the annotations. Um, okay, and then the other question is, well, it's not a real question, but basically it's not an actual worded question, but what would be the Ki of that? And you can use this equation again. P net is basically P frac minus the confining stress, SH mean, 1 times 1 minus over 2 minus 2 over pi times square root of pi L, and you get this 535 psi per square inch. Per square root of an inch, sorry. Notice the weird units for the stress intensity factor and the critical stress intensity factor or fracture toughness. It's basically that's the units that we are dealing with. For it's very hard to get like intuitive units. Many times we get MPa square root meter. So Ki or KIC is given by these units. MPa square root of meter. And the second equation is basically like you see that from Griffith's paper. It's assume a perfectly elliptical shape and so on and so forth. Now, there is at this stage, I think we have knocked down hydraulic fracture initiation quite well. And we have talked a lot about propagation. I can't go too much into hydraulic fracture propagation because it's like, it's not a problem that you can solve analytically very well, especially when it comes to multiple fractures. But I think at this stage, you know enough to follow people who have written their own models about hydraulic fracture growth, etc., etc. And the best example of these people is Mark McClure, who is the co-founder of a company called ResFrac in California, actually. Yeah, Mark McClure was a very, very smart petroleum engineering professor. He was, I think he became a professor at the age of like 20 something. Like he was hired at University of Texas out of Stanford, very, very young. And he had something like 12 students if I remember well, they were like master students mostly. And then he quit. I think 3 years in, he quit. And he went and made a company with an old office mate of his from Stanford. So he went back to Stanford and back to California and made his own company. You have to understand that there is so many software that are being sold every year. Softwares are being made. The fashion back in the mid 2010s was you have a simulator that is doing fluid flow modeling and a simulator that is doing stress and strain, like geomechanics modeling. How do you couple those? You can do something that is called loose coupling, which is to make the simulation go fast, because the results of one simulation affect the other. So you run the codes in a certain way that the coupling is not very strong, but it's good enough for the code to also go fast. That's one thing. Second thing is that by that time, people started writing fully coupled models, models that could do like full coupling with fluid flow and stress strain. But what marked it at the time was he created a model that does everything into one simulation, one iteration. So it's not really coupling. It's one simulation doing everything, both fluid flow and fracture. So this was basically his selling point. And I think he eventually got funded by Altira Group in Houston, if I'm not mistaken, which is a venture capital group based in Houston, I believe. And he did at least 3 rounds of funding, if I'm not mistaken. And right now he's employing at least 20 or 25 people, and including several big names in hydraulic fracture modeling. And I'm not saying that his model is the best or anything. His model is better than several other models that are considered competitors. But in this video that I gave you, that I have here, it's about a 45-minute long video, something like that, or 1 hour long video. And he talks about the physics of how his code is working. And he has a video talking about the physics, a video talking about some numerical tricks that the code is using, and other videos. I chose this one because I think at this stage you can actually follow it. And if you hear it, if you listen to it at your leisure, it will be a nice. I think you're at the stage where you can actually follow and understand what he's saying. So I think it's gonna be enjoyable. The first time I was teaching this class, I got sick and I lost my voice. So I had to find something that doesn't include me speaking for the students. So I chose that. But it was so good and the students were able to follow. So I just kept it in the slides. So because basically what we are going through now is elements that any code for hydraulic fracture initiation will be using. For instance, how does the code work? It's going to be basically multiple iterations in time. So we go time 1, time 2, time step 3, time step 4, time step 5, 6, 7, 8, 9, 10. Okay, so at some point, you initiate the fracture. So you have a notch, a crack notch. Then you measure Ki. If Ki, and you ask yourself, Ki is what? So much, okay. Is Ki bigger than KIC? You say yes, okay. So the fracture will propagate. So the next time step measure, okay, how fast the fracture is propagating, V-frac. What is the V-frac? And then how much is it gonna propagate? It's gonna propagate by delta T times V-frac, the speed times the distance. Okay, so I have how fast it's propagating, in what direction it's propagating, and then I'm gonna basically, excuse me, apply, say, a PKN model, which is a pseudo 3D. I have the height, I have the length, and then I'm gonna use it to find the width. That's it. I mean, V-frag, it can be, that's the velocity at which the fracture is moving. It can be one, that if it's a three-dimensional or a two-dimensional simulation, it's gonna be length and height. And then I can use a pseudo 3D model to get the width. So then I have the new fracture geometry at every time point, and then I go to the next time step, and then to the next time step, and then to the next time step. So basically, this is what he's describing, but with more technical depth. And the audience is like fairly experienced modelers in this video. So when I say module 3, is his module 3. The course that he was teaching is called ResFrac Fundamentals, and he had module 1, module 2, module 3, and module 4. It was a 4-day or like a 2-day event, and that's a module that he was handling, doing the physics, basically. So I have office hours tomorrow. Feel free to come over and bring me any questions you have on the homework, etc. We'll have lecture on Thursday. Homework is gonna be due on Monday, and we will proceed accordingly. So, thank you very much. Have a nice rest of your day.
Thank you, Professor. Have a good day.
Thank you, Shamel. Thank you, Donald.